Um, our next speaker is Andy Wickert from University of Minnesota, who is talking about simulating alluvial river evolution from geological to human timescales.
Thank you, Julia. All right, well, thanks so much to the organizers and to everyone for having me here. And I have the next, let's say, 15 to 20 minutes or so to tell you a little bit about alluvial rivers, some of the work that my group and I have been doing because it's really a group effort, and to hopefully connect the research to some questions that you might have. But I know this is a pretty diverse audience with people who don't think about rivers moving sand and gravel and mud all the time. So for those of you who don't do that, I have a little bit of background as well. Um, and one of the key pieces I want to point out is the fact that alluvial river dynamics are really strongly steered by the changing channel width dynamics, because this sets how much of the floodplain is covered by the water. It also sets the partitioning of the stresses between the bed and the banks on the rivers. So that's something we're going to go into a little bit more. To start out, so just a couple examples for some pictures, since, if we turned around, we might be able to see some alluvial rivers on the plains, but you're all looking at me instead. On the left-hand side, this is the Mississippi River Valley. So it's bedrock walled, but you can see all of these sand and gravel bars that are vegetated moving through, so you can think dynamics of sediment, dynamics of ecosystems, and the two of those connected. And in this case, in a system that's also engineered. And on the right-hand side, actually, this is a photo I took probably back around 2010 with Greg Tucker's former PhD student, Nate Bradley, while doing surveys on the gravel bed at Half Moon Creek up in Colorado, farther up in the mountains here. So we care about them in geology and geomorphology over long term, so over tens to hundreds of thousands of years, actually up to 1 million years on the left. They're shaping landscapes, and so you can see a modern river down here in northwestern Argentina, as well as several terraces, ancient floodplains rising above it. And on the right-hand side is a 1.1 billion year old piece of sandstone that still has ripples preserved in it. So over long periods of time, we can use our understanding of river processes to interpret the geomorphic and geologic past. Over shorter time scales, we can look, for example, on the left, right where we are, right? So this is the circle that we walked through going into Seek. And this is Boulder Creek, which you also might have walked through and might realize that the fact that there's this river here has something to do with the fact that Boulder is here for the river, for the water supply, and also for the ways that it carved the landscape in this low area during integration of the Arkansas River system. On the right-hand side, and I won't walk all the way over there and straight off the stage, but there's a highway bridge you can see on the Minnesota River. And you can see that the river actually seems to constrict right there. The river's in the process of widening, but the highway engineers didn't expect the river to double in width. This isn't something that we usually think about happening. So understanding these geomorphic dynamics actually has a pretty large bearing on how we develop big infrastructure. Because right here, we actually have this choke point in which the river is held artificially narrow. And as a result, during large floods, for example, the water doesn't have space to spread out. So instead it rises. When it rises, it increases the stresses on the bed. It can cause scour, and scour by bridge supports, as you can imagine, might not be a good thing. So geomorphology interacts with our large infrastructure. I'm going to be focusing on self-formed rivers, and so these are rivers that set their own shape in both cross-section and longitudinal profile, and that's pretty common around here in the USA. It's quite a lot less common in Western and Central Europe, where we more or less tell rivers how wide they get to be, but then becomes more common back again in Eastern Europe and many parts of Latin America, and that more or less extends through my world travels. I don't know about other areas. So I'm also thinking about self-formed rivers that are not simply superimposed atop some pre-existing topography, so not just water flowing across bedrock, water flowing across glacial till where it hasn't had enough time to sculpt a shape for itself. These are rivers that have chosen their own shapes. So what are we going to do for the rest of the talk? I'm going to give a 5-minute or maybe slightly less introduction to fluvial geomorphology and river form. After that, I'll really take this larger side journey into thinking about channel width because of its importance in studying river dynamics. Following that, we'll talk about appropriate model complexity, and the short version is that sometimes we can assume that rivers have reached an equilibrium hydraulic geometry and are simply evolving in their slope and longitudinal profiles, so the elevations from upstream to down. And sometimes we might actually have to think about those full dynamics. And then in the last bit, and this is kind of flexibly extended, I'm just going to share some pictures of a field site that we're working on. We're working to develop data sets to answer questions on rivers, both over geologic and human timescales, and to test models. And in the end, I don't have a full conclusion. We don't have the full model data integration yet, but I want to show you the pathway that we're working to get there. All right, so first off, I apologize if this feels too much like lecture slides, but if you like classes, I promise I just made these the other day. And so if you like that, here we go. So on the left, we can see we have water supply and sediment supply entering a river. And the ratio between that water supply and sediment supply, or rather, let's say sediment supply divided by water supply, sets the river channel slope. And the idea, I'll just add in a few arrows, is that if we, for example, add extra sediment, then, and we don't have any extra water, there's more sediment than the river can carry. So it starts to deposit into a big pile. That pile smooths out, and eventually the river has a steeper slope. Likewise, if we don't add as much sediment, then the river starts scouring its bed and reducing its slope until it balances its transport capacity. On the right-hand side, we can look at changes in hydraulic geometry, let's say like depth, width, sort of roughness, although roughness is largely set by the grain size of the sediments entering and by the vegetation. So the rivers will generally adjust their widths and depths to be able to convey the 1 to 2 year flood, and we can see this dynamically in models by people like Weslauer or Kensuke Naito with Gary Parker, where you can add material to the floodplain, widen and narrow, a gradient in size, and eventually you'll find that the combination of flow and sediment transport actually leads to this as an equilibrium condition. So we're talking about sediment moving, and just a quick introduction to sediment transport capacity. Very generically, if we look at the amount of sediment moving through a river, and this is unit of volume per time, we have the river width. So if it's wider, there's more space, it'll move more sediment. And then some function of excess shield stress. So that's this tau star. And you can think about this as a ratio of, in the numerator, the lift and drag forces on the particle, and then in the denominator, the body forces kind of inertially holding the particle in place. And there's some critical threshold that starts that motion, which is this tau star C. And generally, it's raised to some power. I have some values written down there. The tau star basically becomes greater with more depth and slope of the flow. So the more weight of water and the more downslope component, downhill component of that weight. And it becomes smaller as the particles become bigger because bigger things are harder to move. On the right-hand side, I'm just adding in a little thought experiment. So let's say we increase the water discharge, Q. There are a couple ways that the river can respond. One is it can increase its width to hold that greater discharge. And in that case, we have a linear response of the river because the speed term is increasing. The other option is that the river can become deeper. And then therefore it also becomes faster because this no-slip boundary condition of the bed is moving farther down. In that case, we increase the shield stress and the dimensional shear stress. And we then start to activate this threshold, so where we might be higher than this threshold, and activate that nonlinearity. So then the rivers, when they're deepening, become much more efficient at transporting sediment than if they just widen. And therefore, knowing this mode of river response to changing discharge becomes important to understanding the overall sediment transport capacity, which then, as we talked about on the last slide, sets the slope and sets the evolution of the long profile. So here we can take this river at a certain slope again, and if you look over on the right, I have these boxes, and that's just the weight of water in each of those boxes. And you can see if you look on the far right, if there's some water in the near bank area, and we know that rivers aren't, the flow in rivers aren't accelerating, right? We see about 1 to 2 meters per second of water flow velocity in Boulder Creek here, and we don't see something like 400 kilometers per hour in the Gulf of Mexico. We see about the same speed. So since they're not accelerating, we know that the forces must be in balance. And so therefore, the weight of the water has to be balanced by shear against the bed. That's causing flow resistance. In the near bank area, that's against the bed and the banks. And so therefore, that stress is spread out over a slightly larger area. And in the center of the channel, that weight is balanced just against the bed. And this diagram on the right is an approximation. It's not, if we actually ran a numerical model, you'd see some complexity there, but for conceptual purposes, and actually even numerically, it's first order correct. So in this way, we can have, we need to look at this near bank region and think about what the sediment might be doing in the near bank, whether it's possible to mobilize bank material, or whether there could even be sediments from the center where stresses are a bit higher, since they only need to be resisted against the bed. So force per unit area, the unit area represented as the length here is smaller, can be higher. And so taking that to this next slide, we can think about what's actually setting the width, which is the bank strength. And there are a bunch of words here, but essentially, the idea is that if we have higher stress, the walls of the bank can erode. And if we have lower stress, we can actually maybe not erode, but still transport sediment from that middle of the flow where the stresses are higher towards the banks and cause deposition and cause channel narrowing. So on the left-hand side here, there's, we could have bank strength created just by the weight of the grains. And you can think about that like engineers place giant boulders to hold rivers in place. Um, so that's one way to hold a river in place. And the other way to do that is with cohesion. So let's say a combination of clays and their interactions or biofilms or tree roots. And what we find is that the bank strength from cohesion, you know, ranges, but I'm just saying about 1 to 20 pascals. That's just a rough estimate. And nonetheless, if we go look from the rivers on the left to the rivers on the right, basically these gravel bed rivers in which very conveniently this critical shear stress to move gravel in pascals is approximately the same as the grain diameter in millimeters. I just find that to be a nice little mnemonic. So you can think that as long as we're kind of centimeter set grain size or less, we start to become more affected by the bank cohesion. And if we have larger particles, the channel geometry is more affected simply by the weight of those particles and the difficulty of moving them. And folks like Kieran Dunn and Colin Phillips, Doug Jeromack have worked quite a lot on this. Importantly, we're talking about rivers inside floodplains. Once rivers are set inside incising bedrock valleys, those dynamics change because it becomes more of a related rates problem of how quickly is new bedrock being added as land is uplifting, how quickly are the rivers incising. And those can have stresses that are significantly higher because they're being pinned laterally. All right, so those diagrams behind us, I wanted to go back to some pictures. I actually didn't realize that my shoes are in the left-hand picture. So what we have here is a gravel bed river in Colorado, and on the right, we have a sand bed river in Wisconsin. And what we can think about is what's actually holding these banks together. And here you can see there are these particles, there's not so much rooting or vegetation, and so it's really just a physics problem. And I think that this is part of the reason why geologists, geomorphologists, civil engineers have been so attracted to the problem on the left because it becomes simpler since it's more pure physics. The problem on the right, on the other hand, of sandbed rivers and their dynamics has a lot more to do with what's happening in the ecosystem and weathering and formation of that cohesion. And so for there, I think we need to think more about combinations of sediment transport and what's happening inside riparian ecosystems themselves. And importantly, this might be a little low for some of you to see, but if the sediment transport rate is proportional to this bank shear, like cohesive strength, and that is because if the banks are stronger, then that can force the channel to become narrower. Then, in fact, the ecology is in some ways deciding how fast the sediment gets to move through the river. So we have, in fact, a two-way interaction between the rivers and their ecosystems. All right, so just to summarize so far, alluvial rivers set their slopes to transport the supplied sediment with the available water. That's nothing new, at least in fluvial geomorphology. The efficiency of sediment transport is a function of channel hydraulic geometry, so the depth and width. If they become deeper, they're more efficient. If they become wider, they keep the same efficiency. And equilibrium channel width is often set to this threshold for bank material sediment transport. So in gravel bed, once again, it's more of a physics problem. In sandbed rivers, it can be connected with weathering and ecosystem dynamics. And so in the next few minutes, what I'm going to do is talk about when this equilibrium assumption is good or not, and then move on to some model outputs and a few just teasers for a field site. So we basically have two modes of rivers that I want to talk about simulating. One is with gradually varying river discharge. So let's say river discharge varies slowly compared to sort of the decadal timescale of hydraulic geometry adjustment. And in that case, we actually can combine equations which look a little bit large, but in the end, they're really just nonlinear diffusion equations. And we can find efficient semi-implicit numerical solutions for those. And those work as long as we assume that the river essentially keeps up with its drivers in its cross-sectional geometry. And if we think about gradual forcings, that can be things like climate cycles. So this is just showing a 40,000 year orbital climate cycle. And as the discharge rises and falls, we see the river in size and degrade respectively. And here, we're looking just at this purely natural, gradually evolving system. We can also do this with networks of rivers. So for example, on the left-hand side, I've connected this river together in network, and we have base level fall, and there's this nonlinear diffusive upstream propagation of that signal, and that signal propagation is decreasing in speed as we go farther upstream, because near the headwaters, there's less water. And when there's less water, there isn't as much, there isn't essentially as much driving material to cause that river change. We can have something similar with base level rise, or what I think is the more fun one, which is on the right, is landslides. So I'm going to add 2 sediment pulses, and they're going to propagate downstream. And as those sediment pulses pass tributary junctions, note that they actually raise local base level at those tributaries. And so the signal propagates both upstream and downstream through the network. So there we go. Up, and that's starting to flash. So actually, before this gets too annoying, let's just move forward. So, so that's our first mode of river simulation. Our second mode is thinking about the width dynamics. And so what happens when we have rivers that might be able to widen or narrow dynamically. And here, I'm just showing in the upper right, at high stresses, we can have detachment and widening. At intermediate stresses, we might still be able to move sediments around, and they might get stuck to the banks where the stresses could be below the threshold for motion. And then when there's low water, there's low stress, and not too much more is happening. So, although that could be important for vegetation dynamics. And here, for example, I can simulate a river with a full hydrograph and show, in this case, how it's dramatically widening. And this is the Minnesota River, the example from that bridge. So from here, I'm just going to wrap up with one more minute of just like fun slideshow of a site that we're looking at, where we're working to understand rapid changes. So we can look at the geologic record of this particular river catchment. It was also strongly affected by Euro-Americans during settlement. So we have combinations of erosion. We have a farm, and then the farm isn't there anymore. And then we have the house, and the house is too small, and the car isn't working. And then we have things like this where we're going downstream, and this is actually Nila Eastchen, who's back there. He's been involved with the sandbed river modeling. And we can see over here, and Himehas and Rukudapati's in the picture too. See over here, this 2-meter wall is the foundation for a barn. So, and this is Emma Tretton, the master's student, and above, she's standing on the pre-settlement soils, and there are 3 meters of sediment above her feet from agricultural impacts on sedimentation. So, just going to go through these briefly to show aggradation and over time patterns of aggradation and incision through a watershed. And so at some point, I might be able to show you how we can create network models and more broadly understand this. So this is just a schematic model, but I'll go past this to the summary, just so we have time for a couple minutes of questions.
Questions?
Hi, that was awesome. Thank you. I just had a question about the cross-sectional modeling that you were doing. And on the slide, you showed at intermediate flows, there tended to be more likely there was going to be a narrowing in the channel cross-sectional geometry rather than widening or maintaining the same shape. Could you explain how that works a little more?
Sure thing. Yeah, I was kind of rushing past because I realized I spent too much time early on. Yeah, so the idea is that we have, in the center of the channel, we have higher shear stresses than against the channel walls. And so therefore we have both more sediment and transport in bed load and in suspended load. And we also have a higher turbulent lateral diffusivity and than against the walls. And so if you imagine that there's some amount of turbulent mixing and there's a high concentration of sediment in the center, a low concentration on the sides, whether it's because of real turbulent diffusion high in the flow, or because of random walks of bed load bouncing along the bed, there's going to be a net flux towards the banks.
Other questions?
So thanks for the talk. My understanding is this near threshold theory. One of the key pieces is that pretty much all the action is happening at bankful flow. Because when you're above that, there's a floodplain and the water spreads out, so you don't get that much more shear stress above bankful. What are your thoughts about how widely applicable that is?
Yeah, so what Greg is talking about is this near threshold channel theory, which is the idea that most rivers tend to equilibrate to a width in which their banks are near the threshold of motion. So I think that that's the end result to which rivers trend. And I think that we're seeing quite a lot of rapid changes right now, especially in response to climate change and land use change. And so for the idea about flows above bankful, yes, so there for a large amount of additional flow, there might not be a whole lot of additional stress applied to the banks. However, that's I think where we need to couple the the hydrology and the geomorphology. So these flows above bankful will actually be carrying typically suspended sediments, which then start to deposit on the floodplain. And so later in that flood or when the next flood comes, the banks are in fact higher. And so there's a sequence of geomorphic evolution and hydrological change that then resets the river to having a hydraulic geometry where the definition of bankful in fact changes to match climate.
Thank you.